Hello and welcome to this low-level JavaScript series on building parser combinators from scratch. During this series, we'll develop an understanding of the concept of parsing and build up our own parser combinator system from scratch. The system we build will be capable of parsing both binary and text data, and will make use of both object-oriented and functional programming principles to develop an effective and intuitive library. The first question you might actually ask is, what is parsing? Parsing in essence is the process of identifying a certain kind of structured information within data, and in the end producing a data structure that can be used programmatically. Programming languages themselves are usually at the heart of this kind of structured information. While parsing a programming language, we need to be able to understand if the structure we've actually got in the text is correct. And if it's not correct, we need to be able to supply some information back to the programmer, for instance, why it's not correct, as in an error message. And if it is correct, then we should be able to turn it into a more useful form, like a structure that we can interpret. And often the kind of structure that we end up with is a tree. These trees are often referred to as abstract syntax trees, but fundamentally the tree structure mirrors the kinds of structures you see in the text themselves, but in a more organized and useful way. Okay, so the traditional methods of parsing, which you may have come across, especially if you come from a more academic or a computer science background, they're going to center around defining a grammar. And a grammar is the set of rules that describes what is or is not a valid structure. And there are normally different sort of sequence of tokens and or rules, which will many times be expressed in BNF, or back us now form. And back us now form is something that we're not going to dive into in this series, but you can kind of express how these rules work together based on either the tokens you've defined, and tokens are just series of characters, or indeed how they're made up of other rules. So in this form, structures like integer are described as being either a digit or an integer followed by a digit, which allows us to have this kind of recursive structure. And this kind of structure is something that all parsers fundamentally have in common, including parser combinators. The recursive fractal-like structure of the grammar is mirrored in the fractal-like structure of the tree that is usually produced as a result of parsing. So, of course, the series is not about the academic or deeply theoretical approaches to parsing. We're going to be talking about and building parser combinators, which have a much more sort of down-to-earth and pragmatic feel about them. There's a great article by Daniel Holden, which sort of beautifully illustrates how someone could easily discover this technology without any theoretical background. So what are parser combinators then? At the core of it, parser combinators are all about defining small parsers, which parse just a very small structure. And then those parsers are combined together with other small parsers to create larger, more complex parsers, which themselves can be further combined in interesting ways. And the name combinator comes from the idea of combination. And that's most of what we'll end up writing in this series, kind of interesting ways to combine parsing and parsing elements in such a way that we slowly start to build up a description of what we want to parse. Before we build anything, let's look at an existing parser combinator library just to get a good idea of how they work and how they feel. So we're going to take a look at the library arcsecond, which is a production-ready parser combinator library that I've been working on for quite a while now. So let's go ahead and create a new project and npm install arcsecond. Okay, I'm going to go ahead, I'm going to create a new file here called index.js, and I'm just going to bring the entire arcsecond library in as capital A. Okay, so Let's just think of the simplest things we might do. One simple thing might simply be to match a very specific string. So we can make a string parser by using the str function, and it kind of works quite nice because it reads like a string. And let's say we want to capture the string hello. The string parser is now a parser object, and you can see it here. What I'm going to do is I'm going to console log the result of running string parser. I'm going to call the .run method, and I'm going to provide it the string hello. And we'll just see what comes out from that. So I'll go ahead and run node index here down in the terminal, and we'll see that it is not an error. Error is false. The result is hello. The index is 5, and data is null. So basically what we got here is an object which describes the result of our parsing, and it was obviously successful because it wasn't an error, and the result was the string hello, which is not that interesting since that's exactly the string we put in. If we try to match the string hello world, that's also going to work because we do actually match the string hello, and that's all our parser said to do. So even though it doesn't get to the end of our total string, we do sort of get to the end of our parser. We can obviously put in something that isn't the correct word hello here, and if I run that again, now we're going to see a similar object, but this time we're going to see that error is true, and the error itself is going to be parse error position 0, expecting string hello, but got world. So the index here that we're talking about, so the index 0, basically that's talking where we got into this string, how far we got, and it's kind of like the state of where the parsing is up to in that string. So we failed at world because we literally couldn't get past the 0th character. Whereas if we use hello, we're actually able to get all the way up to index 5. Okay, so there are other kinds of parsers. You can match strings, but you don't always know what you want to get from a string. So we can use something like letters. And now letters will let us capture letters. So here we're able to capture hello just the same, but now we can also capture world. And how could this cause an error? Well, if we provided this some numbers, for instance, then we're going to get an error because we're expecting some letters and we got numbers instead. We can also just get a single letter. So we might have a whole word hello, but here we're only going to capture H and we're only going to get to index 1. Likewise, we can capture digits. We can try and throw some numbers in here and we'll capture those. And if we try to have letters in there, we're going to fail. Maybe let's take a little look at a Parser Combinator at this point. So here we might want to get, again, the string hello. And here, if we take our example string and we duplicate it a bunch of times, so we have a bunch of hellos in there, and we run this, we're only going to get the one. We're not going to match it over and over again because we haven't told our parser how to do that. But we can use a Parser Combinator, so a parser which takes another parser as input and returns one that can do something more. We can use the many combinator wrapped around our string hello, and now we can match that hello over and over again. And you'll notice here what we got is an array. The output of this parser is an array, and every item is one of the things that we captured inside. Now that's not that interesting if we capture just hello, but if we were trying to capture something more interesting or something more complex, then it would be useful again for us to have that. So what we could go ahead and do here is we can separate these two. So we can say, we can pull this out here and we can say the hello parser, and we can plug that in here. What we can do here is we can use another combinator. So here we'll use the Choice Combinator, And what choice takes is an array of parsers. So we'll parse it in an array here, and we'll use our original string hello. But I'm going to add another one in that's called world. And so now what we're saying is that this parser, the hello parser, can either parse the string hello or the string world. So now what we can do is we can come here and we can type hello, hello, world, and we should be able to match this just the same. And you can see here we've got our individual elements here. So now we've already managed to get something a little bit more interesting. Another interesting element of parsing, or of parser combinators, and this is not the case in every parser combinator library. This is something specific in arcsecond. You can, for instance, say, okay, we're going to match the string hello, and then we can actually call .map on that. And that's any kind of parser, and this description is wrong. This is still trying to read the array method map. And what this map does is it takes a function that receives the result of parsing, and we're able to transform that in some way. So what we can do, for instance, is return result.toUppercase. And so now, if we parse the string hello, our actual result is hello. And we might choose to also, reverse this. Oh, of course, yeah. Reverse is not an actual string function, so we won't do that. But what we could also do here is return a more complicated data structure. So here we could already return, let's say, an object who has a type captured string and who has a value, and we'll just use the regular result. And so now what we've done here is we've returned the same thing, and we haven't changed, but now as the output we have this more complex data structure. You can map the result of every parser, so we can also take the result of many, for instance. So we can say a.many, and we can map the output of that, and that's going to give us values or results. And what we might want to say is take all those results, which are strings, we know they're strings in this case, and we'll just join them together. Let's first map them. So now we're mapping the array itself, and we'll call x.toUppercase, and then we'll join them all together, and then let's just duplicate this a few times. Of course, it's toUppercase, not uppercase. We've captured and mapped the output of what was before an array. We've joined together into a single string. So that's quite useful. Obviously, you want to be able to capture more complex things than this. Most interesting structured data is going to be sort of a sequence of things. We can actually easily do that with a sequence of, which also takes an array of parsers, just like Choice did. But now we might want to do something like this. Let's first capture some letters, and then we'll capture also some digits, and then maybe we'll get the string hello, and maybe we'll capture a character, which is the space character, but maybe we get many of those. And then eventually we'll finish off with the string world. And what we can say here at the end is we can say end of input, which is a special parser which only matches the end of the input. And it of course can't give us a value, so we'll just see null. So here, if I type a bunch of letters and then I type some digits, and then we have the string hello, an indeterminate amount of spaces, and then the string world, If I run this, what we'll see is the result is an array. And that array is going to mirror the structure of this array. We're of course going to have one result for every one of these. So we first capture our letters, then our digits, then we get our string hello. We capture a bunch of spaces, and because we use many, here we actually have an array within the array. And here we have world. And finally we get a null value, which just represents the end of input. So you can see that already. If we throw an exclamation mark on the end there, we'll get an error because we expected end of input. Now, something to notice here is that this is already a tree. We could arbitrarily wrap any section in here in a sequence of, for instance, we might want to say that the first two parsers are actually one single sequence, and we treat them as one thing together. It doesn't change the structure of parser, but it does give us a different result. So here now our first result is also an array with these two elements. And we could map this, for instance, as we're running, and we could say results, and actually maybe we only want to get the second part. What we have is just the string 1, 2, 3, 4. So we skipped the letters because we ended up removing them, but we did parse them. Okay, so I'm going to create a small function here, and I'm going to call it tag. And tag is going to take a type, and then it's going to take a value. But what I'm going to do is I'm going to curry this function. So I'm going to make the function return a function that's waiting for a value, and then eventually we'll do something with it. So it's two levels. And the reason I'm going to do this is because we're going to be able to feed this function partially applied to map. So the idea is that what we're going to do with tag is just take the type and the value and put them inside an object. It's very simple, but what I want to do here is I want to map, and I want to map it to a tag, and I'm going to name this tag letter digits. And so what's going to happen here is when map runs, it's going to run this function. So it's going to feed the value, and that will come in. And type is already provided by us here. Okay, I'm going to space this out for clarity. And then we can tag this, but I'm just going to tag it as a string. I'm going to tag this, but I'm going to tag it as whitespace. I'm going to tag this as a string. And I'm going to tag that as the end of, I'll do it in camel case since I've done the rest, end of input. Okay, and now if we run this, we can see that we already have a sort of tree structure. And we could map the whole output actually to, we'll just call it our tree. And so now we have a result with a type our tree and a value, which is an array of further branches of the tree, further tags. And it could be, for instance, that we're mapping this many, and I'm going to space it over a couple of lines. We could also map the tags here and call them a space. So we've called this whole thing white space, and this is just a space. And what I'll do here is I will, let's see if I just run the result. Okay, so here the final output is that we have the tree, we have our value, and we have all of these. And inside white space, though you can't see it, there are also further tags. So we've created our own tree structure out of this. This is a little bit of a messy parser, and there are many nicer ways to do this, to split it up, to take, for instance, this whole thing out and to create, we'll call it a subparser. And here this would act exactly the same. And so we could, organize our whole our whole parser this way. And so you can see that we can build parsers out of smaller parsers. This is a parser built from 2 smaller parsers, which itself goes in as a small parser to part of a larger parser. And this is the way parser combinators work. So that should give you a good idea about how parser combinators work. There are many different ways that these combinations come together. If you check out the arcsecond documentation, you will see many functions here, and we're going to go into them in more detail in later episodes. This has been primarily to introduce and develop an understanding of what parser combinators are and how they can be used. In the next episode, we'll begin with the implementation of our own system. If you've enjoyed this episode, please consider subscribing for future installments of this series. Otherwise, thanks for watching, and I hope to see you next time.